Okay, it's getting towards 2 o'clock, at least in Central Europe. And of course, there is other timings around the world. As you would have read, we're attending the third edition of the ISPRS Keynote series. As you know, it's a webinar. We already see the title of the third presentation. Let me say that it's a very recent addition to the ISPRS services. My name is Christian Heipke. I'm serving as ISPRS president at the moment. And I'd like to not only welcome our speaker, Monika Sister from the Leibniz University Hanover in Germany. Good you're here, Moni. Not too far away from where I'm sitting, but we meet virtually more than physically these days. I'd like to welcome everybody around the world, of course. I'm seeing the number of participants is increasing as we speak. It was 3 or 4 just half a minute ago. We're up to 47 at the moment, at least this is what I'm seeing. And I'm sure we've had pre-registrations, a few hundred. It's 2 o'clock now, so maybe we can do a little small talk before we actually give everybody the possibility to then also get the start of our interesting presentation called Capture and Interpretation of Mobility Data. Maybe I'll say a few words about our presenter today. Monika Sister is, of course, a professor of cartography and geoinformatics, as I mentioned, at Leibniz University Hanover. She's been with our university for some 2 decades or so. Her education is in geodesy and geoinformatics. It's from Stuttgart and obviously before that from Karlsruhe, 2 cities in the southern part of Germany. Monika has been active in ISPRS for a long, long time, but she's one of these people where one organization isn't necessarily enough. So she's also been active in ICI, our sister society, International Cartographic Association. And when Monika becomes active somewhere, it means she becomes active. So she's been vice president of ICA for a number of years. She's also been active, and you already know what that means, in our university administration for a number of years, looking after international relations, international issues at the whole university. At the same time, she has a very dedicated, a very clear, a very outspoken research record in aspects of cartography. Generalization is just one item she's been having a big impact in. Geoinformatics, data structures, use of spatial data, and more recently, she's been involved in mobility, in mobile data, and things which move. And I guess that is pretty much what we're going to hear from her today as well. Moni, the floor is yours. We're all looking forward to your presentation, Capture and Interpretation of Mobility Data. Thanks for doing this.
Yeah, thank you very much, Christian, for this kind introduction. Thank you all for attending here, at least virtually. I just imagined how it would be to see you all, and I think I'm longing for that by now. So after 1.5 years of this semi-lockdown, even if it's convenient, I'm missing you. So therefore, I think we have to do the best, and I hope I can somehow entertain you or give you some information about our research that we are doing at our institute, dealing with mobility data. So mobile data, mobility data is data that captures the movements and the mobility of objects in general. And objects could be people, like here, a crowd waiting to enter a public space, or here crowds in the main station, but also mobility of animals that also show certain characteristics, certain patterns that we might be interested in. And of course, nowadays, exactly these days, this is also an important mobility aspect. And the more mobile they are, the more entertaining it is, namely soccer, and observing and trying to interpret and to predict what soccer players are doing is also something that we have been dealing with. So mobility data usually boil down to trajectories, and these trajectories can be captured with different, basically also news sources, namely these GPS trackers that are everywhere these days. And basically they capture a sequence of points. So we have X, Y, and possibly the height, and a timestamp. And this is the basic element of trajectory. But of course, we can also enhance this by additional information that, for instance, the moving object is carrying with it. So a sensor that is moving captures, of course, its trajectory, but also the information that it gets from the environment with its sensors, such as a LiDAR or a camera. And we can capture trajectories of vehicles, of pedestrians, of soccer players, of animals, of the environment, like a hill that is sliding might be such a dynamic object, but also in the street environment, it might be a dustbin that is moving or moved to another place before it's getting emptied by the public service. Okay, so how can mobile objects be characterized? I took this view graph from the book of Matt Duckham on geosensor networks. And I think it nicely describes how the data occur and in what shapes they come. So we can describe the movement of objects as being unconstrained. So this object may take any trajectory here in space and time. It can also be, on the other hand, restricted to a road network, for instance. So it can only go along this road, but not across here. Another distinction could be according to the discretization of the measurements. So the measurements could be taken every whatever length or every time, once a certain time has passed. But also it could be according to checkpoints. So only at certain checkpoints here visualized with junctions, there's a measurement, and in between you do not have any measurements. And the third distinction could be done whether the sensing is done by the sensors themselves. So they are moving objects and they have the sensing capability, or if the moving objects are observed by a set of static objects. A set of static cameras. So these are distinctions that we have to keep in mind because they influence on how the shapes of the trajectories look like, and also how dense the trajectories are that we can deal with. So let's look at some examples of general trajectories. As I said, they can describe a restricted movement, and restriction could be in terms of the transportation network. We see here an example of trajectories that cars have provided, and we see that it's a motorway intersection. We see here trajectories of people that walk on certain paths, and we can also immediately see that some of them are more popular than others. And also trajectories of bus fleets can show us where the buses typically go and exactly, more or less, exactly delineate the routes. And this is also what we can do with such kind of data. We can kind of digitize roads, routes, but also popular paths, and identify them in this way. But we also can find out if there are changes, if new roads are built or others are abandoned. Or we can also look at the traffic rules that underlie that overlay the road network, and which is visible in the behavior of the user of that. Other examples for restricted movement is the behavior or kind of lifestyle. And here's an example of animals, namely seagulls, that have been equipped with GPS. And we can see here how these animals spend their lives, at least the lives during which they had these devices on. So obviously they are based here, but they are flying around quite wide, quite long. So they go out here to forage, for instance, to look for food, but also for mating and whatever. So the animal ecologists are very interested in such trajectories in order to get more insight into the behavior of animals. Okay, so mobility data, as I said, is representing the movement of objects. It's spatial temporal information. And I also want to extend it by, it's also information that is sensed by moving sensors. So dynamic information or information that gets the dynamics of the environment. And what we can do with it, our goal, what do we want to analyze? We want to know what is the movement behavior. We also want to predict it. We want to detect specific behavior patterns. And also we can use such kind of data to capture and update our environmental information. I want to focus in my presentation on the dynamics of objects and the environment in a traffic context. But before I move to traffic, I think I cannot go without looking at a very important topic these days, namely the European Soccer Championship. And in this direction, Udo Feuerhake, one of my team members, has worked on his PhD thesis. So he was looking at what can we do with a bunch of trajectories like these black lines that soccer players leave during a game. So if you all overlay, you should just see nothing. But of course, there's a lot of structure, at least usually, structure, tactics, and ideas in these movements. And the idea of the football analysis that Udo devised was to find out some patterns. So find out individual movement of players. So why did this player run in this way? Or to identify the movement of a group of players and then find out something about tactics, and also find out about sequences of how they play the ball to each other back and forth in order to also predict next passes. So in essence, it deals with pattern recognition, but in this case, the problem is that the definition of a pattern as such is not given, because it could be a pattern that a person runs in this way because it's very specific for one player, but you would not think of this as being a pattern beforehand before you would recognize it. So therefore, the definition of pattern that Udo was applying was a pattern is something that is appearing several times during a game. So it's a frequently repetitive movement. And with that definition, he's able to look at and to identify, to reveal patterns, as I showed in the previous slide. Just to give you an insight how this can work. So he's using a trajectory and is analyzing the whole trajectory in a moving window approach, and kind of decomposing this trajectory into a sequence of individual movements or locations or positions. And by transforming the trajectory into such a sequence of individual items, it's possible to use classic methods, in this case from sequence mining, to analyze these patterns. So how could this be? One idea is to just take the points as sequence items and come up with a list of points. And then the goal would be to find exactly in this list a repetition of the same sequence of points. If we take just the points, then you can imagine that this hardly allows any variances. So you have to find the exact points again. We can relax this condition a little bit by allowing translation, by coding not the points, but the distances between the points, so these movement vectors. And we can also encode the angular direction and also allow rotations. And once we have these vectors, we can now try to apply such sequence mining algorithms. Of course, we are not exactly using these items that are defined, but trying to cluster them in order to also accommodate for some uncertainty. So not the individual items that have been on the previous slide are used, but some clustered items. But then the goal is to have such a sequence of individual items, and we want to find sequences of the same patterns, like the repetition of this blue, red, and green pattern that comes again in the later sequence. And there are algorithms around, for instance, the a priori algorithm, and Udo implemented modification of it. And what the algorithm needs is the minimum length, namely the number of items in a pattern, and the minimum frequency. So how often does that pattern has to reoccur? How many reoccurrences do I need? And using these algorithms to the different parameterizations he has allows, on the one hand, to find patterns or lines, trajectories that are very similar in location. So obviously, this is a strategy of one player to start in that corner and run off it in this direction. So, and you see here the variations that are allowed in a certain degree. If we also allow translations, then we see that this pattern occurs here, it also occurs here, and it occurs there. So obviously there are runs, passes that players take that are typical for them, and they reoccur. Another pattern that might be interesting is something with to detect passes. So the fact that in this case here on the left-hand side, player one starts, he gives the ball to this one, and he kicks it to that one and goes back to the first. So this is a sequence that obviously occurred more often in the data set, namely 3 times, and the length is 4 in this case. And here there's another pattern that also occurred in the data set, namely one player shoots the ball to this one, to that one, number 3, back to this one, and up to that one. Then the ball continues in a non-regular way. So you see, it's possible to find patterns that have not been defined a priori, but patterns in the sense that they are repetitive and they reoccur and they can be recognized again. And in this way also used to predict the behavior. So I wonder, I'm not sure what we can predict for tonight, but at 6 o'clock our local time, we will see how our match goes against England. Okay, so now let's move to the more traffic-related topics, and I will continue in showing you examples of research work of our staff. And I will start with capturing the infrastructure or the environment and its dynamics. And this is work by Julia Schachtschneider and Klaus Brenner. It deals with information that we have to provide for autonomous vehicles or assistance systems. And you all know that these systems, they need very precise map information, so-called high definition maps. But the problem is that our environment also changes. So it's not only the changes that occur because there are some constructions and renovations, but it's also the daily changes, like the changes between day and night, between the seasons, or the fact that in front of the school, there are different situations when you go in the morning, in the afternoon, or in the evening. So humans are very good at coding this information. So we are familiar with these facts. We know how a situation looks at night, or we can at least imagine it, even if we have never been there before. And in order to equip an automatic system with such a kind of information, we also have to enrich the maps with that kind of dynamics. In that way, also the machines can have an expectation of how an object might change from the situation as it is in the map to the current situation that is available. Okay, how can we determine such dynamics maps? We do have a mobile mapping system. It's a Riegel VMX 250 with 2 LiDAR scanners, precise positioning, and also some cameras. And we get LiDAR point clouds of that nice density. And what Julia did, she did a data capture campaign every 2 weeks over a whole year of a track of a length of around 20 kilometers in different areas of Hanover. So this is the distribution over these this year. You see that it's over the year, but also during different times of the day and also times of the week. And in that way, we get a good distribution of the situation of the environment during 1 year. So here you get some ideas about how the environment looks at different seasons, different weather conditions, but also different traffic situations. And then the idea that she has is overlaying all this information may reveal the dynamics of objects. And you can see it here in these images. Each run is coded with one separate color. And you can imagine if all the colors more or less overlap, then this is a static situation because all the rays hit that object. And if you see objects only in one color, then you can imagine that this green colored car was only visible or standing there while the car or measurement car was running here once. So in this way, it's possible to analyze the situation and come up with a discretization of the space in terms of a voxel grid, where we can identify voxels as being hit by a LiDAR beam or missed. And let me briefly explain the underlying idea. It's a ray tracing approach. It presumes that all the different measurement runs are adjusted. So all of them relate to the same points. So in this situation here on the left, if the car goes around the first time, then beam will hit the facade of the building, and next one also here again, and here again, but the next beam will not hit the facade, but the car which is parking there. And therefore we do have some hits and also a hit on the car. But if our measurement van comes by a second time, it will again hit the same voxel here, here again. But now it won't hit this one because the car is no longer parked. Instead, it will hit the facade and it will go through this voxel here. And we call those voxels that are kind of shooten through by the LiDAR beam, we call them as a miss. And the other ones are counted as hits. And just counting the number of hits and misses already gives us an information about the statics and the dynamics of the environment. You see here, the higher the number of hits here, the more static the objects are. So these are the facades. And what is in blue here are the dynamic objects, so the cars that are standing in front of the buildings here in the foreground. Therefore, it's indicated as less number of hits. And here we see some glimpses of the ground. And the other way around, it's the number of misses, where we see that a high number of misses is the object in the foreground, namely the dynamics of the environment at the level of the capturing car, namely mainly the pedestrians and also the cars that are standing there and no longer standing there at another instance. Okay, so having this information allows us to kind of separate the voxels into static and dynamic. So the gray ones are the static ones and the colored ones are the dynamic ones. And this also allows us to clean our environment and get rid of all the dynamics and make it more smooth. And the same also for larger environments. Of course, we have here a section of several roads that we can clean with respect to the dynamics object. So the idea, as I said in the beginning, is that we want to have maps for autonomous driving. The points have an accuracy of 2 centimeters. That's static information, but we also now have information about the dynamic objects. And what Julia is currently working on is to find out about the temporal structure, the temporal behavior of these dynamic objects. Here's another example that where the dynamic point cloud has been used. It's done by Torben Peters, and he was exploiting the data set that we have, namely that our measurement van is able to capture both the LiDAR data, so creating a 3D point cloud, but also corresponding images. And what he did, he used a so-called GAN, generative adversarial network, in order to synthesize a colored image by only providing a point cloud. So the idea is that the system gets a lot of examples of the connection between a 3D point cloud and an image, and then automatically learns to colorize a 3D point cloud. So given a colored point cloud without color, the system is able to synthesize it. And if you look at it, it looks quite realistic. Although if you directly compare it to the real situation, you see there are some discrepancies. So the color of the facades is not the same, although it's a typical gray. And also the cars, they have their typical color, although this one, which is given in cyan, is not synthesized as the original one. Obviously, the system has seen more gray and white cars than these very colorful cars. So what Torben did in addition, because we do have data sets all over the year. So his idea was to have another construct, namely a conditional generative adversarial network, by including also the season into the network. And in this way, the idea is to also be able to take a point cloud, inject a date into this network, and then create a seasonal representation. And this is what comes out. We have here a winter situation, and here's a summer situation, all generated from the same point cloud. So only giving a point cloud and a date, and then the system synthesizes how winter looks in Hanover, with a little bit of snow here, and how summer looks when you have more green in the trees and also the vegetation around. Okay, so let's move on to some traffics, some routes and characteristics of traffic objects. And this is a project that is done by a couple of people. They are dealing with bicycles and all the application, or a lot of applications that can be done in that context. And Oscar is especially interested in looking at the comfort of riding a bicycle. So you all know that cycling, at least in Germany, it's getting more and more popular. In some countries, it has been popular for a long time, but in Germany, it's rising popularity. But some of the infrastructure is not as favorable as we would wish. And one criterion that people often have is that they want to ride comfortable routes. And then the idea is how to make maps where the comfort of a route is devised, is delineated. And the idea of Oscar and his team is to collect data with an app that they developed. And this app is able to measure the acceleration components and can just be installed on the device. And then users can do their daily rides and at the same time capture these acceleration parameters. And the idea is that this acceleration is a proxy for the underground. So if it's rough, then you have more accelerations, and if it's smooth, it will be more smooth. The problem is, however, you do not want to, there is no single rider that is willing to capture all the information. So you probably have a lot of bicycle riders that capture this information. And you can also imagine that the acceleration, so our measurement, will depend on different factors like the type of bike, the type of rider, whether it's a heavy or a low weight person, how many pressure is in the tires, and so on. And this will also influence the accelerometer, so the measurement that you're doing. And in order to combine it anyhow, the idea of Oscar was to use an adjustment approach. So the idea is that, first of all the data are related to a road network, which is in this case taken from OpenStreetMap. So we have individual road segments, and all the measurements that are taken by the different users are then mapped to these individual road segments. The roughness score is taken from the acceleration, and especially using the median absolute deviation. That is taken as an input for the adjustment process. And yeah, the idea is that since we have individual segments that are visited by several cyclists, each of them has different accelerator meters, but they are observing the same physical process, namely the roughness of the surface. And therefore, the goal is to estimate this unknown roughness by using all the observations of the individual users. In this observations, or in the adjustment, we also take into account these different criteria that we had, namely the bike, the rider, the tire pressure, and so on. The result is as such, so we get a map where the roughness is indicated here in different colors. And we see here a little screenshot of the result, where we see in green is the smooth roads, and in red is the more rough roads. In the park, we have a little bit less smoothness, which is nicely corresponds to a reference that we have from OSM, where the surface type is given for, at least for some roads. And for those, you can make the comparison. We also see that here in the area, which is denoted by a B, that OpenStreetMap says this is a wonderful asphalt road, but our measurements tell that obviously this is not as smooth as asphalt would assume. Okay, what do we do if the environment changes? And the idea is that this can also be detected using this approach, because people are using it over and over time. And then we can, for instance, also identify temporal effects. And here's an example where we have some measurements here that are obviously varying due to the different users, but they are all in the range of, let's say, 3 to 4, around 3 in this roughness measure. But then at a certain time instance, they are dropping to a very much lower value. And obviously, there has been some reconstruction work, which we can see here nicely. But the question is, how do we identify it automatically? And what Oscar did was to apply an OTSU segmentation that we know from image analysis, gray value separation, that can also be used in order to differentiate between these two distributions, maybe the higher value and the lower one. In this way, it's then possible to segment also different temporal or different situations in the environment where the situation has changed. And now, obviously, only those values should be used for the calculation of the roughness. Okay, so let's continue with another example where we also need trajectories. And in this case, Stefan Busch is looking at how to define high definition maps from laser scanning. This would be the goal, that we want to have very precise axes, left and right borders, and also the stop lanes and so on. And he is looking at the lane axis. What he does, he uses a scanner. He installed a Velodyne scanner at a junction and was observing the cars that pass around. And with a semantic segmentation approach, we was able to determine the classification of these cars and also the segmentation of these cars. And then they can be plotted. You can see how the dynamics of this object is. Of course, these individual objects at certain times have to be concatenated to form trajectories. And this is done using a Kalman filter. And after that, he ends up with small snippets, small trajectories of elements that a car has passed. And those now have to be combined to the road network. And this is done by using a Monte Carlo optimization approach, which is somehow visualized here, where we take the individual snippets and then try to align them in a way that fits to the model of a junction, so that joining snippets are nicely joined, that they have certain properties and so on. In this way, he is able to get and reconstruct larger pieces of the road network by individual observations of cars. So what he now found is he analyzed his trajectories with respect to ground truth and found out that there are some discrepancies. Most of them are in the range of half a meter, but there are also areas where we have larger values. And one reason for this is that the car model is not modeled as a full car, or that the sensor only sees part of the car. And what he did, he just took the more or less the center point of the point cloud that was visible. And this leads to a systematic deviation of the car. And therefore, his new model was to take an active shape model in order to fit that to the point cloud, in order to better represent the shape of the car and therefore also the center point. And using this model, he's now able to better delineate and also create the bounding boxes of these cars and therefore the center points of these cars. And from that, the trajectories, and finally from those, the inference to the road network. Okay, so using this active shape model provides, even if you only have one aspect of the cars from the LiDAR that was standing more or less here, it's still possible to derive the center lines. So we get less error, so less red areas if you go from left to right. And also the mean deviation is now from around 60 centimeters down to around 40 centimeters. Okay, what else can I offer? Yeah, one research topic that Hao Cheng is working on deals with prediction of behavior of people in shared spaces. So if you look at such a situation, of course it's accelerated here, but you have a situation, especially in shared spaces, where different road users coexist. So you have cars, you have cyclists, you have groups of people or individuals. And the question is, how do they behave? How do they take care or to respect, give way to the others? This is obviously very essential, especially when it comes to automatic cars. They have to interact with normal, ordinary people. And so they have to know how they react and how they are expected to react. And to this end, Hao came up with a deep learning approach where he took into account that a mobile object or pedestrian, a car driver, or a cyclist, they have a certain intention why they go along, but they might change it abruptly. Also, other agents will affect their behavior. Most of all, they do not want to collide into each other. So, and this influence of other agents is dynamic. And therefore, Hao was coming up with an approach that also can compensate for this dynamics of the other objects. He also used a concept that is able to predict not only one deterministic trajectory, but several trajectories that are also capturing the variability that is in these possibilities. And to that end, he used a conditional variational autoencoder. And in that autoencoder, he also included so-called dynamic maps that are able to capture the object in the immediate neighborhood, namely this is the ego user, but he's influenced by other objects around. So the positions of these other objects, their orientation, and also the speed that they have, all will influence in which direction or at which speed that person will proceed. And that is coded in this interaction mechanism or attention mechanism that is originally has been developed for natural language processing, but has been reused for several problems where such sequences and learning from sequences is very interesting. And so he also was learning the sequence of these interaction between different users. The whole network looks as follows. So it's an autoencoder model that takes the trajectories, also the ground truth into account, and creates a latent space where we have the mu and the sigma of these variables that are being predicted, and based on them at inference time, not only the positions can be predicted, but also the variation of these positions. Hao was quite successful on a state-of-the-art benchmark dataset, the Trajnet dataset from Stanford, I think. And you can see here that at least I think that's 3 months ago, that his system was the best on this list. So the least average displacement error of the prediction versus the ground truth. We can also see that his approach was on the list again, where he tried without these dynamic models, and we see the improvement is considerable here. Yeah, we are talking about slight improvements in all these lists, but it's 1 centimeter in the average displacement that is considered as considerable. So let's look at some situations where we have images where the trajectories are taken, the ground truth is given in black, and then we see multiple predictions in cyan, and the most likely prediction is given in red. And we see that we get the kind of bunch of possible trajectories that all make more or less sense. We can imagine that people have different possibilities to go along. This is also interesting here in the lower left, where we see 2 people walking towards each other, and you know the situation where you do not know whether they should go right or the other goes right and left and so on. So this is nicely also reconstructed in that data. He also applied it to another data set, which is more related to car traffic, but also here it produces very nice results. So for instance, here in the lower left, we see a situation where a pedestrian is on the crossing, and the car is giving way by standing there and keeping its position, so not moving or only slightly moving. You see it here. Okay, so Hao has finished his thesis, but he's thinking about next work, what he could do. And one element that is for sure quite relevant, at least for humans, it's quite relevant, namely the scene context. So where, which areas are passable? Where could I step on? Where could I walk on? And the approaches up to now, they use it, but it tends to overfit. And the question is how to include scene context without sacrificing the generalizability. But this is something that he will surely also look at. And one other idea is what also is often tackled in the context of deep learning is to combine what is known in terms of rules, for instance, and neural network models in terms of a hybrid model. That also seems to be quite promising. Okay, let's look at another example of research work done by Yifeng. He is looking at precipitation and whether that can be learned from traffic speed patterns. So of course, what we can observe is that if it's starting to rain, the cars are driving differently. So they are typically reducing their speed. And now the question is whether that could be used. So the adaptation of the speed, whether that can be used as a kind of precipitation indicator. Of course, it's not meant to be a replacement for weather stations, but it was more or less a proof of concept to find out to what degree that can be extracted. So what he did, he used a data set from New York City, where they have 133 roads that are equipped with speed detectors. And every 15 minutes, there's information how fast the traffic flows on these sections. So what he did was he linked these data with information about precipitation from the Weather Underground API. And this way had a connection between the traffic speed and the precipitation. As I said, people adapt their speed according to the precipitation, but obviously the speed also depends on other effects, like there might be seasonal trends, there might also be weekly or daily trends that are available. That are in the data, and therefore he first of all got rid of this trend using the Profit software from Facebook, and then found out the discrepancies between the predicted speed and the observed one. And he said, okay, in these discrepancies, we do have the anomalies that are possibly due to the precipitation. And this was then his input for the machine learning, where he exploited different state-of-the-art machine learning methods and found out that Xaboost was the best. We see here that there's an overall very high accuracy. And just to give you a visualization, so he created a binary detector, so precipitation yes or no. This is given in red here, and in blue you see the true precipitation. And we see that in general there's a very good overlap. So there is precipitation here, and our system also told so. Here we have precipitation. There are of course also some positions where the system predicted a precipitation, but there was none. So here and here. And we also have the other way around, that there was some precipitation, but the system did not detect it. But overall, quite high, also F1 score, so for precipitation, around 80%. The system also, Xaboost also allows inspect the importance of the individual observations, individual roads, and found out that obviously there are some roads that are more important, more indicative for precipitation than others. And in a system that could, for instance, be used to especially look at those roads in order to determine our predictor, namely whether it's raining or not. Okay, so my last example is a little bit more cartographic. It deals with visual communication of routes in this case, so also trajectories, but routes. And what is the underlying idea? So the idea is that if you have more and more traffic, and that's probably everywhere around the world, we will also face consequences like congestion, air pollution, noise, more accidents, and so on. And the idea would be that if not all the people would take the same route, but would more disperse, then, or if they would take into account that their traveling also has these consequences, then we would have less of these consequences. So if people would not all drive the same road, then the road would not be congested so much. However, drivers typically, they prefer routes that bring them to their target destination on the fastest way. So if we are faced with this situation, I'm starting here, want to go here, then probably I would take the fastest way here and not go around here. But the question is now, how could we kind of nudge the users towards taking the little detour in order to benefit for the whole society in terms of having less congestion or less noise or less air pollution in this area? So this is the underlying idea, that we can use cartographic visualization to visually communicate that this might be the better for everybody, even if it's longer for the individual. So taking this into account, we see that there are some attempts. In Germany, there's a navigation company, Nunav, that tries to not always send all the users to the same roads, but do some variation. And what Stefan Fuß, who is doing this research, recently found out is that Google has a new feature, at least they announced it, that not only gives the fastest route, but also the most fuel efficient route, and also gives a value according to the CO2 footprint emission that is lower than the other one. So this confirms us that we are right on track. But what Stefan is trying to do is to use visual means to make also the seemingly less favorable route look attractive. So I think we are used to such visualizations that do not exactly correspond to the reality. So for instance, looking at these schematic maps or destination maps, where we see that the reality is often highlighted or exaggerated or schematized. So why not also use it for route recommendations? And therefore influencing the users to be more altruistic in their behavior. So how can we do it? We have obviously the classic vocabulary of what we can do. We can use the graphical variables that have been determined by Bertin and extended by other researchers later on. So we can vary the intensity of the routes. We can use icons or different forms. We can use color. We can use the size, enlarge routes that we want to emphasize, and so on. But we also can use the coordinates that are also one element of the graphical variables. In this case, kind of deform or enhance or generalize the routes in order to make them more visible or communicate what we want to have. So how did he do it? How does he do it? He calculates, he uses the road segments and calculates for each segment a relationship between the observed value and the threshold. So if there's high density here, then this leads to a larger R value, and this would mean this segment is not recommended. And if in this case, the density, but you could take also particulate matter or whatever, if it's lower than the threshold, then this would be lead to a smaller R value, and this would lead to a recommended route. And based on these R values, then different variations of visualization can be created. So to give you an example how the position, the X and Y coordinates can be used in terms of distortion of the length. So if you have a situation where the traffic is very slow, then you get the impression that the distance that you are covering is longer. So the perceived distance is much longer than the actual one. And in the other direction, that's true as well. If you are running very fast, then you perceive the distance as being slower. And that's coded by lengthening segments that are driven slow and shortening the ones that are driven fast. So that's one possibility to exaggerate the true route, which is given here in black, to the one that is given in red. Or another way to use the kind of cartographic generalization is to simplify and distort route segments. So in this case, the ones that are driven very fluently, very fast with a low R value are simplified. So you get the impression that you can go very smoothly. And the ones that are difficult to drive because there's a lot of stop and go, they are exaggerated by giving a very distorted shape. Okay, in this way, Stefan created different design variants, also taking the color, the U value, the spacing, also symbols, and the ones I just described, like the distortion, or here the size, the width of the symbols as possibilities. There are also other possibilities that kind of noise can be applied. The distortion we already saw. We also can apply it not only to the line, but also to the underlying areas. And using the color hue as an example, we can also use transparency or blurring. And we can also use icons that can be overlaid both over the individual line, but also over the area. And this way, we can have different further modifications, like here, different U values. Here, this distortion. So the preferred, the recommended route would go around here, and the one which is not recommended would go straight ahead. But since it's very distorted, people should get the impression that it's better to go around here. Same here, using areal object, it could represent either the speed of travel that is possible in that areas. It could also represent the noise level or the level of particulate matter, and all should indicate that better not go here, but better go in the green or blue areas. Blurring can also be used, and the idea is that people get the impression that it's safer to go around here than in this blurry area. What he's also currently doing experiments with is with emotions. So people look at visualizations and they immediately link map symbols also with kind of emotions. And so for instance, with congestion, you could have a positive emotion that when the traffic is nicely flowing, that you're relaxed, calm, contented. And if it's not, if there's a low traffic flow, then you are stressed, nervous, tense, and so on. And using symbols that code these emotions may also lead to kind of nudging the people to a certain behavior. So here we see an example where this danger symbol is used as a background, and hopefully it also leads to the fact that people say, no, I better go around here instead of going through this danger zone. Okay, he did a study with more than 100 participants. I think it's not here, but it was a lot of participants. And he did the study based on the experiments he did with the lines. And what was the result is that obviously the distortion had quite a beneficial effect. So people recognized that and they chose those routes and preferred the distorted ones towards the ones that have not been distorted. So obviously there the system worked out. Also, the symbols were quite positive, received by the people. The size did not have the expected effect. There are some limitations in his ongoing work in his PhD. So it could be that the route choice also depends on other features, that people take other features into account, not just the visualization. And also the visualizations as such, whether they are accepted is not yet tested, only whether they have an effect. But if people would look at it and accept it and would follow then the visualization in a concrete decision situation, that also has to be studied. Okay, so this brings me to my last slide. I want to summarize that obviously mobility is essential, and mobility data is essential for understanding humans, their behavior, and also their environment. And we need it for several purposes. I think I could show you some of them. Those mobility data are available nowadays abundantly. And they can be captured with different sensors, including the human as a sensor, or our cars or our vehicles as sensors. We need a lot of data. I think you all know, and you've had a presentation in this series already about deep learning, where you probably learned that those systems need a lot of data. But there's one caveat, especially when it deals with people or people-related data, that data is also intimately linked to privacy aspects. And this is a challenge that is beyond the technology and beyond the algorithms that we might devise. Namely, how can we convince people to share their data, even their trajectories, if it's for a good purpose. So important public purposes like prediction of travel, making the traffic more fluent and so on. I think that could be beneficial, at least for many people. But that could be a research strategy as well. How can we ensure that personal data can be used for the benefit, but still be protected, and that privacy is preserved, because that's a very important good. Yeah, with that, I want to conclude, and thank you very much for your attention. I think I stopped my slide, because then I can see more of you.
Okay, well, thanks very much, Monica. Very nice presentation. I hope you can all hear me. The communication is still going on. Yeah, you can see that mobility in today's world is kind of an important item, right? And you can also see that when people talk more about mobility, the result is going to be interesting slides, because mobility is not only in the content, it's also on the slide. Things move during the presentation, which is, of course, something which catches attention of the attendees. And I think that was a very good example of both the importance of mobility and the way how that messages can actually be transmitted. Now, it was a presentation by a professor of cartography who knows how to influence people, as the last example vividly showed us too. With that, the floor is open for discussion. I just posted a little sentence in the chat box. If you have any questions to Moni's sister, please don't hesitate to let me know. There is a few reactions, I should say. Thanks for the wonderful presentation, which goes to your credit, Moni. We have the same in German, which I'm not going to read out loud either. But then if you want to hear anything else about the topics addressed, that is your chance now. So don't be shy, just go for it. I've opened my chat box wide and large so that I won't miss anything here. Who is going to dare sending the first question? That's always a little difficult. Here is one from Pavel. Thank you very much for your excellent, inspiring presentation. Do you have any experience in indoor tracking? I wonder if the precision of data collected using inertial measurement units in mobile devices is sufficient for pedestrian tracking and indoor localization applications.
Yeah, no, I don't have experience in indoor. We did have a students project where we had some indoor navigation as well, but this was done on a very coarse level that we used QR codes. So at certain instances, the users were supposed to take a QR code, and with that they would localize themselves. And the way you are alluding, taking inertial measurement and so on, I know there's a lot of research around, but we do not do it, unfortunately. I think it's very interesting and very relevant to go indoor.
Okay. One could imagine it kind of depends why you would be wanting to track pedestrians. There may be different accuracies necessary and also levels of completeness with different applications, maybe privacy, security, you know, trying to warn people that they shouldn't step into something more dangerous, etc., etc. Okay. Thanks for the excellent presentation. Any suggestions or comments on mobility behavior studies related to the pandemic? A very up-to-date question here. Any suggestions? Have you come across anything in that regard?
Yeah, so there are a lot of there's a lot of research done in that direction. Just today, we have a guest scientist at our institute who is a statistician, and he was investigating the effect of different factors on also on particulate matter. And there he also looked at data before and after the lockdown, where he investigated this based on also mobility data, but also measurement stations that could measure these effects directly. So there's a lot of work in that direction, and I think that's also relevant, and where we also can show that our research, namely spatial data and the dynamics of spatial data, is very relevant to also tackle problems that are very dominating these days and also in the future. Thanks for that question.
Yeah, maybe to add on, this is going to be my first commercial with respect to the ISPRS Congress, which is of course going to take place next week. On the Friday of that week, which means on July 9, there is a roundtable on geospatial data and health, which will certainly cover that topic as well. If you want more information, how to link, etc., visit the website or just send an email to me. I can give you more information. Well, that's the end of the commercial of the first commercial of the Congress. Any further questions to our speaker on capture and interpretation of mobility data? Here is another one. Thank you for the nice presentation. Will map distortion cause information overload for the user while using map navigation?
That's also a very interesting and relevant question. So as I said, what Stefan did up to now was just looking at how these concepts were perceived, whether people would choose the alternative that we want them to choose based on the way the visual variables have been applied. But you are now asking, how would that be in the real context when they are in a navigational context? And this is not yet investigated. And it is the crucial question because it's meant to be there. On the other hand, we are also thinking that this route choice is something that you do before you start. So you type in your destination and then you get the choice and then you say, okay, I choose route 1 or route 2. And it could be that we might then turn to the normal routing visualization and not these exaggerations that we use when the person is offered the 2 options or the 2 or 3 options and select one. But this is a very important topic, and Stefan has it on his to-do list, but I'm not sure if he really will make it during his PhD, but it's important. Thank you.
Okay. Any further comments or questions? That one was closed. Wonderful presentation is another comment here. So here comes my second commercial for the Congress next week. One of the applications which Monica Sester just presented, namely the ride vibration, so the way to determine the roughness of the underground using these bicycles, has been selected as one of the best young author papers for next week's Congress. This is going to happen on the Wednesday afternoon. So I think it's before noon, sorry. And this is all related to European timing. So I understand that Oscar Waage himself is going to give that presentation. If you want more information on that one, tune in next Wednesday when Oscar Waage is going to speak, I believe at 11 o'clock in the morning. So that was commercial number 2. I hope to have given you a little more time to think about additional questions here. I don't see anybody typing at the moment. No. I'd like to pick up on your last topic where you said how to convince people that they should share data and so forth. That's, of course, a very, very big topic in itself, which is far beyond or somehow removed also from geospatial data, etc. My first answer would be trust. And the second one would be incentives. Now, with respect to trying to tell people to take the longer road, so your last example, you had little incentives there as well. Do you have any experience what works in these areas and perhaps what works better than others? If you were to create trust, if you were to provide incentives in such mobility applications, which you have shown, how would you actually do it?
I think people are, they like incentives, or they accept some sacrifices if they get something in return. So if I consider myself, I give away my position for Google Transit because I exploit Google Transit so much. So I think it's worth, and since I'm using it so much, I want to give something back. But and I think that might work, that people will get engaged in actively giving away their data is a problem that is often discussed in VGI research. So for instance, there might be some applications that observe catastrophes or situations like heavy rainfall and so on. And people might easily come up with and say, okay, let's create an app and people will use it and they report when something of those things happen. But then our observation is that people are not willing to install a new app and to provide this information, and they would not do it quickly enough. So exploiting data sources that people are serving anyhow is something that that is quite promising. So this opportunistic VGI. But of course, then people should somehow give their consent. Also, they should be aware that that information could be used also for other purposes. And that touches the notion that you had, namely the trust. And I think if people know that nothing bad happens with their data, then they might be willing also to trust. Or if they see what happens with their data, if they see the benefits that are drawn from their data, that might also increase the trust. And on the other hand, I think it's always good to make your to not get users tempted to explode more out of your data than you would be willing to. So it might be good to leave the data on your device and not spread it too widely, or to have mechanisms that that allow that it's kind of protected, privacy preserving algorithms. There is also a lot of work in that area.
Okay. Now there is a whole explosion of questions coming in over the last couple of minutes here. I'll try to cover at least some of them. From Mahmoud Reza Delabar, Monica, could you please explain how quality will affect mobility data and analysis?
Yeah.
General, but important, I'd say.
It's important as everywhere, where we need, at least we need to know the quality of the data in order to exploit it in a reasonable way. Of course, quality will determine what you can do with the data. If you have only a very sparse spacing of the trajectory of your car, then you would not be able to do some elaborated inferences, for instance, on I did not report on that, but I also have a PhD student. She is working on inferring rules, traffic rules. So where do people stop? Is this probably a yield sign, or is it a red light, and so on? In order to infer that kind of information, you need high quality data, very dense spacing, and also related to the spatial accuracy. So it's always an issue that you need to know the quality, but once you know it, you can know what kind of applications can be done with it.
Okay. David Hollett from OSU would like to know, noting that your examples are rather localized, how they would scale to national level.
I just wonder what is
difficult, not so easy, right? I mean, maybe you were never shooting for scaling up to national level with the examples you've shown, rather than trying to give new examples. But it's, of course.
Yeah, but let's take the first example I had with the mobile mapping. So the idea is, of course, we had a very elaborated mobile mapping system. And you will not have that scaled over the whole world if you're not Google, and not even Google has that. But our idea is that the future cars, or the current cars, already have a lot of sensors on board, and they will make it with the sheer mass. So we have a lot of sensors that are available, and by that we can also eliminate some of the quality problems that we had in the previous question. So get more quality from the lots of the data. I think we can use the same principles that have been shown by not taking one measurement system that goes around every 2 weeks a year, but having several systems that are permanently on the road and try to make the same inferences. So in that way, I think it should be scalable. Of course, it depends on the measurement systems that they are available. But if you're relying on like speed cameras, they might be available in some countries. Yeah, of course, yeah, the cyclist example, there you also have to rely on people who are using it. But since it's an app that could be used, or that the acceleration can nicely or can easily be extracted, that could be something once people are convinced that sharing data is somehow beneficial. But that's a prerequisite, you're right.
And then bikes typically cover a smaller area anyway, like compared to cars, etc. So yeah, interesting. Here's another note which challenges you with a new possibility, shall I say. Paul Newby notes the following: the old maps nudged people by representing the nature of roads reasonably accurately. My cottage in Wales is on an extreme minor road, single track with no passing places, etc. Now, Google and SatNav have discovered that we are on the shortest route from north to south Wales. And we know what's going to be the consequence. Paul continues, we have far more traffic than ever before. Please, and that's a pledge to you and to everybody who's in that area, please nudge people back to the main roads as quickly as possible. Thanks, Paul, for that statement. And well, maybe you want to comment on that too, Monte.
That's a very good example. Hi, Paul. I hope you're doing well. Yeah, that's right. Cartographers have done that ever since, and the technology also does sometimes things automatically that people would not have done by themselves. So obviously visualization helps, and it's not only visualization that is inside Google and others.
Yeah.
But it's the data, and getting that out of the systems again might be difficult. But if it's OSM, you can do it yourself, right?
Yes, you make them a little smaller again. Maybe put a road construction there, Paul. Or, I mean, another thing you could do is simply dig up the road. Then the rest will follow automatically. Change the real life. Which brings me to another question here. I'm trying to capture as much as I can. Thanks for the nice presentation. What do you think about combining virtual and real mobility? So digging up a street, therefore blocking traffic, was that an example? Or what do you think about combining virtual and real mobility?
I'm just trying to think what you mean. So we do have virtual mobility now when we are all sitting at home, but we are at a joint conference. So perhaps you should elaborate a little bit more what you mean with virtual and real mobility.
Okay.
It's not quite clear for me, but of course the pandemic has shown us that some of the mobility that we usually did because we thought we had to, we can eventually drop because it's not so necessary. But some of the mobility is necessary. It cannot be replaced. Mm-hmm.
Here is another one. Can you comment on the potential of existing GIS in smart handling mobility data and perhaps indicate future directions in computing movement and analyzing that movement? So potential of GIS data. Maybe you read those things as well.
No, I didn't find it now.
Okay. Well, if you open your chat box, it's on the question from Mahmoud Reza.
Right. I saw it. So you mean existing GIS software? Obviously. Actually, I'm not. Of course, you can program everything with existing GIS software. I'm not too familiar with that. What is available just on pushing a button, but of course you can implement it. No, I'm not aware. Sorry for that, Mahmoud.
Okay. Thank you for your great presentation. In fact, utilizing LiDAR data is too expensive. Let's say very expensive. Definitely for large areas. Do you think it would be applicable for tracing vehicles in a city? You know, I mean, you're really giving an answer when you say too expensive. So I guess really the question could also be interpreted in the way whether there is alternatives or there is better, cheaper, whatever alternatives tracking vehicles in a city.
Yes, probably there is. We like LiDAR and try to exploit the data sets, but you are right, they might not be available, and definitely, so what the example I showed where we have stationary LiDAR might not be something that is scalable, but you could also imagine that, as I said before, our cars, they are full of sensors, and the sensors get better and better. We also have imaging sensors, cameras that produce stereo. So you could get 3D point clouds also from stereo that the cars have, and there you are. So I think it's possible. The cars will have some LiDAR sensors. They will probably not be as good as either the one we have on our mobile mapping system, nor the one that is that has been stationary. It was a Velodyne 64. But with 4 or 10 beams, that could also help for some applications. So I would not be so pessimistic as you cannot scale it. But you're right, for the time being, LiDAR as such might be too expensive.
Okay. Maybe a last one, which may be a little difficult to answer, but it doesn't matter. The question is, can we make a new type of virtual reality model using more realistic data, such as extensive virtual reality? So virtual reality with more realism, I think. So using all the data which you have acquired.
Yeah.
Or, you know, you people are in the status of acquiring.
Mm-hmm. Yeah, I think that's an interesting question. Although I know the notion of extensive VR is not, I'm not familiar with, but how I interpret it is to have even more information in the sense of augmented reality, but perhaps all the available information, including the dynamics. And I think that is very, very much interesting, because eventually also a user might have the need to exploit that information. So I imagine, for instance, sitting in a car, and it would be perhaps nice to be warned that somebody is coming and will not stop before he or she is crossing the road in front of me. And getting that information in terms of augmented reality, but perhaps also other mechanisms that might hide under extensive VR, that might be very beneficial. Of course, we need some devices to also visualize that, to see that. In a car, we could have a head-up display. There are also these glasses that Google has been promoting some years ago, and now Facebook is also developing these glasses. I'm not sure if we all want to wear that, but definitely it could help at least some aspects of safety in traffic.
Okay. I guess we've covered just about at least most of the questions, all of those which I was able to kind of take note of. In case I missed one, that's your chance to put it in now. And while you think about it, there is one question which is a little different. and that is whether attendees will obtain certificates for the attendance. Now, normally we don't do that. If there is a good reason to do so, I suggest you just send me email, explain why you would need that certificate for, and then we can see whether we can help. We can help you. In general, this is not really what we're doing. And maybe a final one. What do you think about big mobility data and data mining in future driverless car industries?
Yeah, I think that is what will be happening. So at least I am looking forward to having autonomous cars. I think that would be beneficial, at least for me when I'm getting older. For people who are not as mobile as they have been, but also people who are not willing to drive. I think that that is a promise that we have, and that's only working if we have a lot of mobility data, a lot of data available, and that has to be gained somehow and in some ways, and be provided in a reliable, privacy-preserving way. So there are a lot of challenges on that way. Besides legislative aspects, and also aspects of trust. How will we handle such systems? How will we feel when we sit in such a car, and how will others feel when they stand outside the car? So there's a lot still to do, but technology is advancing, and I'm looking forward to that.
Okay, now the explosion of questions is somehow coming to an end somewhat. And maybe we've exploited your time long enough now. It remains to say another thank you very much, Monica. I think we've seen a colorful bucket of very interesting topics, interesting and relevant topics of today. Soccer was there, bikes, coloring, I should say the winter into summer. That's I like it more in that direction than the other way around, but I might be biased. VGI. And you have, and that's why I'd like to point it out as one of the last things here, you have kind of hidden the solid mathematical foundations. You haven't really spoken in detail about optimization. You haven't really spoken in detail about the details of deep learning. About parallel computing when it comes to scaling, about big data, about spatial temporal data analysis. All that, of course, important, complicated topics in themselves is all needed in order to come up with such nice applications, colorful, moving slides, etc. I'm saying that because sometimes your presentation came across as being entertaining, as you did say in the very beginning. And yes, entertaining it was. I'm trying to remind people that below that entertainment, there's a lot of very complex science. And you have shown to me and to everybody here that, and I knew that beforehand, right? That not only are you able to give a great presentation, thanks for that, but it's only possible on the basis of such solid science. So I think we had a very successful session, therefore, today, number 3 of the ISPRS Keynote series. This now is going to be the 3rd part of my commercial with respect to the ISPRS Congress. I hope you can all see that. July 5 to 9, next week, we'll have the digital edition of the 25th Congress, which physically would have happened in Nice had conditions not prevented us from doing so. So I hope to see you all next week virtually, as today. Things work nicely. And the last applause is yours, Moni. Thanks very much for your great presentation. Thank you, and thanks for everybody attending.
Thank you for having me.
Well, we're glad you've been with us. Okay.
Okay, yeah, thanks. Bye-bye. See you.
Thanks a lot, and bye. Goodbye then. I'll just leave that on for the time being, okay?
Okay, ciao.